Okay, hello everyone, and welcome to this 31st online Spintronic seminar. The speaker today is Dr. Matthew Daniels, who is an NRC postdoctoral fellow in the Alternative Computing Group at NIST. He earned his bachelor's degree at Clemson University and PhD at Carnegie Mellon. His dissertation work was on antiferromagnetic magnon physics, and his postdoctoral studies include multiple topics in neuromorphic computing, which is a bit of a new topic for our seminar. I don't think we touched upon this before. And Dr. Daniels's work was focused on new ways to encode information to bridge the gap between traditional CMOS engineering and the novel capabilities of magnetic and memoristive nanotechnology. So his talk today will be about brain-inspired computing using Spintronic technologies, and I'm giving it over to you, Matthew.
Great, thank you. And thanks everybody for being here. I'm really pleased to be able to share this work with you, mostly based on a paper that we published earlier this year, which was about using superparamagnetic tunnel junctions as fundamental functional elements for a hardware deep neural network. So I think this talk, as Carl kind of hinted at, is going to be a little bit different than many of the talks that I've seen in the seminar series so far. Much of what we did was an applied physics project. You know, we had a Spintronic device and we wanted to use it to do some kind of interesting computing. And I know I've been guilty many times in the past of coming up with an interesting physical device and assuming the engineers will take care of the rest, but we wanted to actually take care of the rest ourselves. We wanted to know what it would take and what it would mean to push the Spintronic device from just being this physics system into a full-fledged system where we could make mature estimates on things like area and energy so that we could compare it to existing technologies, but maybe more importantly, so that we could really understand the value that the Spintronic device was giving us in the broader context of electrical engineering and computer architecture and circuits and systems. So this talk will be more like a narrative in some ways of what our journey was like, overcoming our hubris as physicists to make it to that point where we were interfacing with engineers. But before we get to that, I want to back up and just talk a little bit about why we're thinking about making a neural network and what the metrics were that we wanted to reach in terms of making a computer that is neuromorphic, that is shaped like the brain. So the field of machine learning is really where all of this starts out. We all know that machine learning has been a big deal for probably a decade now and can do some pretty amazing things. Machine learning is good at cognitive computing tasks. It's good at doing tasks that the human brain is good at doing. That's why we study it, because we're interested in computers interacting with us in human ways in our human world. The picture here is from a now famous competition from a few years back, where a computer system called AlphaGo beat Lee Sedol, a world-ranked Go player, Go master. I think 4 games to 1, it beat Lee. So this really highlights to what great heights the algorithmics and mathematics of machine learning has come to be able to achieve this feat. But at the same time, there is a story that's not really told when you're just listening to how great these algorithms are. At the physical level, the computing cluster running the AlphaGo computation is drawing 100 kilowatts of power. Lee, who's basically a normal human, his brain is drawing 20 watts of power. So despite the fact that it was able to match and even slightly exceed his ability to play this game, there's no way to really reason in a detailed fashion about physical resource utilization from being so high up in the clouds at the algorithmic level. And that, I think, is part and parcel of how computers work. So engineers think of computers as being layers of abstraction stacks. So at the very bottom, you have physical devices. You have silicon, you have wires, you have transistors. These are all physics systems. And we think of them as physics systems. It's not until somebody decides to establish a mapping between physical state and logical state. It takes somebody saying, when this wire is grounded, it means 0. And when this wire is at high voltage, it means 1. And at that point, you kind of have the basics of a computer. Now, once you do that, you start to realize you can use the physical dynamics that takes you between physical states to do computation in the logical space, in the mathematical space. And so you build simple primitive operations like AND gates and OR gates, all the basic logic gates that underlie everything the computers are doing. And then you put those together into complex circuits to do things like arithmetic and so on. But once you're at this level of the circuits, you don't need to be, and you certainly don't want to be, reasoning about the material properties of a MOSFET transistor. You want to be totally insulated from everything that's lower than you in the stack. And you also don't want to be thinking about what version of Python somebody is using when they're calling your circuit. That should be irrelevant to you. So engineers have established these various abstraction layers with clean interfaces between them. We all agree on the interfaces, but then you can work on each of these layers independently. And that's what allows the entire field of electrical engineering to improve computers over time without any one person understanding every single component of a computer. Now, in terms of machine learning, all the progress has pretty much been made at the very top. That has started to change as people have realized that they want machine learning to be involved in more and more parts of life. It has become worthwhile to drill a little bit deeper into the stack and optimize what would otherwise be architectures and circuits that are useful for general purpose computers. People have started to specialize them for applications in machine learning. So people, I'm sure, are familiar with graphical processing units. I think it's even come up in a few of the tutorials in the seminar series. These are great at doing linear algebra. And so you can use them to carry a lot of the workload in machine learning, which is highly dependent on linear algebra. Google has developed something called a tensor processing unit. It's kind of a brain-inspired type of computer that can do machine learning calculations very efficiently. And as people have specialized deeper and deeper into this stack, they've been able to get better and better energy efficiency on these tasks. So case in point, AlphaGo was acquired by Google, and AlphaGo's descendants are now running on these TPUs, which have been specialized for machine learning. And that's brought the power consumption of these devices down by 2 orders of magnitude. So by going down into the stack and optimizing things for machine learning, you can get really big power and area savings. Now, as physicists, it's not really our business to play around up here, but it is our business to play around at the bottom of the stack. And the idea of introducing new devices with interesting nonlinear or stochastic or oscillatory behavior to sort of try to provide new foundations for realizing different types of primitives and circuits that might be more like the brain. I'm going to broadly refer to that effort as neuromorphic computing. Now, if you want to build a computer that's shaped like the brain, neuromorphic, you need to understand at least a little bit about how the brain computes. So at some level, the brain is just a biomolecular machine, right? It's running on quantum chemistry and statistical mechanics. There's probably nothing useful to learn at that level about computation. So what people do is they zoom out and they think of coarser and coarser grained models of the brain until they finally arrive at the model for computation in the brain that's based on spiking neural networks. So this is the idea that the brain is basically a directed graph. All the nodes of the graph are called neurons, and they have ion channels that go from neuron to neuron, and the neurons can send spikes of electrical potential down these ion channels. And when a neuron receives enough spikes from other neurons in a short enough period of time, it will itself undergo a nonlinear process and generate new voltage spikes that propagate to other neurons. So we know that this, spikes flowing around all over the place is happening in the brain. Seems like that's probably doing some kind of computation. It's not completely understood. But one question we can ask right now is, why does the brain use these spikes? Now, I'm not a neuroscientist, so there are probably good biological reasons, but at least from an energetic perspective, the brain is a statistical mechanical machine. It's wet, it's noisy, and you need some kind of signal that can be seen above the noise. So high amplitude signals are ideal for that. And if you want to minimize the energy of a high amplitude signal, you of course want to shrink the time over which the signal is generated. So you end up with spikes. So that's one view on why spikes used in the brain, just to have an energy efficient form of communication in the presence of noise. Now, people have kind of known about this for a long time. And by the way, people now think that computation in the brain might even be more complicated than this. But just thinking about these spiking neural networks, one thing that people decided to do a long time ago was zoom out further to an even more coarse-grained model, a simplified model, a model that's, a physicist could have come up with it, where we make a lot of simplifications, but keep the essential behavior. So the first simplification is that we make the graph acyclic. We don't want any feedback loops. And we make it nice and layered. And what that lets you do is end up using matrix multiplication to get from layer to layer. It's a little bit complicated, but not relevant for the talk. The other thing you do is you assume that the information carried in these analog spike trains has nothing to do with the precise timing of the spikes or with the amplitude of the spikes. What you decide is that the important thing is the rate at which spikes occur, the probability of finding a spike at any given time. If you agree that that's the important information carried in one of these spike trains, then you don't need an analog spike train. You just need one number to represent that probability. And thank God, because computers are much better at doing arithmetic with numbers than they are solving, analog differential equations. So people realized this and started to build these artificial neural networks where a neuron would output just a number that represents its spiking rate. It would get multiplied by some weight corresponding to the probability of successful transmission along these ion channels. And then a neuron downstream would add up these contributions and apply some nonlinear function that's supposed to stand in for the nonlinear integrate and fire behavior of neurons in the real brain. So that's an artificial neural network. Those are the backbone of most of today's machine learning. So this is a really important model that a lot of people are interested in. And it's based basically on linear algebra and scalar functions. Now, what we were interested in doing was, the brain is communicating with these spikes for a reason, but we know how to train and operate these simplified neural networks. So maybe we can keep the same layered form, the acyclic form, but instead of sending numbers from neuron to neuron, we're going to go back to sending spike trains. Each neuron will associate with a distribution, some random process that outputs spikes with some probability. And that probability will be the information we're trying to encode. And somehow we'll take joint probability distributions to multiply these things together and then have some interesting function that happens at the neuron to combine these input spike trains into some output spike train. So that's the idea. And where this all comes back to Spintronics is that we needed a way to efficiently generate these random process spike trains. And the way we do that is using magnetic tunnel junctions. So I imagine the audience largely knows what MTJs are, but just in case, I'll quickly review. The simplified model here is that an MTJ consists of two ferromagnetic layers separated by thin insulating dielectric. Now, through the magic of material science, we arrange for one of these ferromagnetic layers to have its magnetization fixed permanently in one direction. And the other magnetic layer is given an easy axis so that it has two stable states, one parallel to the fixed layer and one anti-parallel to the fixed layer. Now, it turns out that because of magnetization dependence in the way electron orbitals overlap in the tunneling barrier, you get different tunneling probability depending on the orientation of the free layer. And so that lets you convert magnetic orientation data into resistance data, which is much easier to integrate into modern electronic devices. So one of the things that drew us to MTJs is the fact that they're really mature devices. People are manufacturing these now, and not just academic labs, but real companies are making devices with this technology in it. They're integrated into industrial fabs. And industry is even starting to explore new things to do with these devices, just like we are. So Intel last year announced that they were looking at using MTJs for memory like right next to combinational logic, not long-term memory, often something like a hard drive or RAM, but memory sitting right next to logic gates. So people are really interested in these, and there's a lot of money flowing into this field. And what we're starting to see is that there's a whole spectrum of different ways you can use MTJs. And one big knob you can turn is the energy barrier between the two stable states of the free layer. So if you want to use an MTJ as a memory device, you put a really big energy barrier between the parallel and anti-parallel states. And you do this because you don't want thermal events to accidentally corrupt whatever data you're storing in the MTJ. Now, if you're doing something like Intel is, where you're using it for short-term memory that needs to last, maybe dozens of nanoseconds, then you only need a retention time that's on the order of milliseconds, and you can get away with a smaller energy barrier. The smaller energy barrier is advantageous here because even though the large energy barrier prevents thermal fluctuations, it also makes it harder for you to write the device into a new state using coherent current. So lowering the energy barrier gives you lower write energies. But for this talk, we're going to push the energy barrier between the states even lower, as close as we can towards KT, while retaining a two-state device. And this is what we're going to call the superparamagnetic regime. So this is a stochastic magnetic tunnel junction, and we think of this device as exhibiting random telegraph noise in the magnetoresistance. So the switches between its two states, as long as it's a two-state device, pretty much follows what's called the Nail-Brown model, and is something like two interleaved Poisson point processes. So, while you're sitting there in the anti-parallel state, the amount of time you have to wait for a transition to the parallel state follows an exponential distribution with some characteristic switching frequency that corresponds to the anti-parallel state. And the same thing happens when you're waiting in the parallel state, but with a different characteristic frequency. Now, with an ideal device, you would imagine, and we do assume this, that these frequencies are about the same. So you're mostly spending half your time in each state. But what you can do is pass a current through the device to create a spin transfer torque on the free layer. And when you do that, you partially stabilize or destabilize each of the two states. And you can actually make it more likely to find the device in, say, the parallel state or the anti-parallel state. Okay, so we knew about all of this. This is known physics. But what occurred to us was that if you look at just the transitions, they kind of look like those spike trains that are flowing through the brain. So our thought was, can we use these to communicate the way the brain does, and then build some kind of computer that's operating on these spike trains generated by the MTJs? So that was our idea. You have this telegraph noise and the magnetoresistance. You could use some simple circuit to turn it into spikes. And, bonus, since you're spending less time in the high voltage state, you're going to use a lot less energy, right? Because if you're not in a high voltage state, there's no current flowing. So this is what we thought. And maybe that's because we're physicists, or maybe it's just because we're theorists. But some people in the audience, I'm sure, will know that this is absolutely wrong. We just didn't understand how CMOS works, how computers work. So for the benefit of those who, like me, didn't understand this, I'm just going to review it in one slide with the example of an inverter. So in your computer, if you have a bit, right, the bit A, it could take the value 1 or 0. It's either in a high voltage state or a low voltage state. And you want to apply a NOT gate. You want to send a 1 to a 0 or a 0 to a 1. The way this works is by controlling switches. So if this bit is high, it will open this switch so that there's no path connecting the high voltage source to the output. And it will close this switch so that the output is connected to ground. So we've successfully sent a 1 to a 0, but note there is no current path that current can flow from high voltage to ground. So there's actually no ohmic losses in CMOS, in traditional computers, except for the infinitesimal time during the transition between low and high states, and a little bit of leakage current due to the fact that these aren't ideal infinite resistance switches when they're open. So what we learned is that in CMOS, it's transitions that cost energy, not steady state holding at a particular voltage. Which means that we don't really want to do this. In addition to the fact that it would have cost extra to make a circuit that turned the random telegraph noise into spikes, it's also the case that we would have used twice as much energy because we would have made 2 transitions every time one transition happened in the random telegraph noise. So we learned our lesson pretty quickly about that. We were wrong about how energy consumption works in CMOS, and decided that we would try using probability coding instead of spike rate coding. So we've already diverged from how the brain works, but it comes down to the fact that the fundamental environment of how energy is produced and consumed in the brain is different from how it is on a chip. So we had to come to terms with the fact that while we can take inspiration from the brain, sometimes taking it too far actually leaves you in a worse spot. Luckily, computing with these probability-coded bit streams is actually something there's a whole body of literature on. There's a field called stochastic computing that deals with computing using time series of random ones and zeros. The poster child for this stochastic computing field is the AND gate. And let me show you why. Imagine you have a random bit stream coming into the 2 inputs of an AND gate, and that bit stream is high with probability P sub A and P sub B on the 2 inputs. Well, as long as those are independent random processes generating your ones and zeros, the probability of finding a 1 on the output is going to be the product of the input probabilities. So you're doing multiplication of 2 numbers with a single AND gate. That's really power efficient, and that's really space efficient. An OR gate also has some interesting functionality. For low probabilities, you kind of add probabilities together, but of course you can't exceed a probability of 1. So there's this nonlinear correction that becomes relevant when the probabilities, when the input probabilities are large. So these are some basic ingredients of stochastic computing, and we decided that we would use these to build the functional elements of our neural network, where the inputs and numbers are all being generated by MTJs. Now, we haven't discussed yet how you actually get these voltage signals from the resistance signal of an MTJ. And one way that's done in the literature is through a circuit called a p-bit, which is a pretty ingenious circuit. You have a stochastic MTJ, and remember I told you that when you run current through it, you get a spin transfer torque on the free layer, and you can control the probability of being found in the P or AP state. So you can kind of tune these statistics by using an analog input voltage, and then you get some output signal that looks like these various types of bit streams. The problem with this device is that you are constantly, experiencing ohmic losses because you're running current through a resistor all the time. Now, at first, we thought, big deal, there's always current running through computers. But then we learned how CMOS works and realized we were wrong. And actually, this is inefficient compared to how most CMOS logic gates work. Now, maybe that's just the price we have to pay for using stochastic MTJs. But we started looking around and realized that people had a scheme for reading out the states of MTJs without using constant currents. And the way that's done is with something called a pre-charge sense amplifier. So I'm not going to go into transistor level detail about how this works, but just to reinforce the idea of current not needing to flow to do a useful computation, I want to give you a basic model for how this circuit works. So the idea is that you have a parallel circuit with an MTJ and a resistor. And the resistor has been chosen so that its resistance lies between the 2 states of the MTJ. You've got all these switches sitting around, and some of these switches we're going to put on a clock. So when the clock ticks, we suddenly close this switch and open these switches. Now, when we do that, instantaneously, in non-equilibrium, there's a little bit of charge still sitting in these wires because the wires have a finite capacitance. This switch has a finite capacitance. They're real devices. So we know what will happen to that charge. It will discharge down to ground. But these charges have to go through resistors. So there's going to be an RC time corresponding to each of these branches that will govern how quickly the discharge happens. So we let things discharge, And let's say that the MTJ is in a high resistance state. So all the charge discharged from this branch first. Well, we detect when this wire hits ground, and as soon as it does, it switches the other branch. And now the other branch has been connected back to the voltage source, whereas this one has been connected to ground. We're back in a state where there is no current path from high voltage to ground, but we've detected the state of the MTJ, right? If the MTJ was in the low resistance state, then these would have opposite voltages because we would have switched these guys instead of these guys. And then once we're done with this, we can reset the circuit so that on the next clock tick, we can detect the state of the MTJ again. So it was Weisheng Zhao who came up with this idea for sensing MTJs originally, but very recently, it's been used by a few groups to energy efficiently detect the states of superparamagnetic tunnel junctions. This, by the way, is the more exact form of the circuit based on transistors, and this is an analog circuit simulation. You can see the red path discharges a little bit faster than the blue path, and then the nonlinear feedback of this thing switching the gates causes the blue path to go back to high voltage while this guy discharges. So we wanted to use this instead of a p-bit because we wanted to push energy efficiency. That was our idea. The brain is energy efficient. We can be too. But we didn't know exactly how energy efficient this was a priori. So we brought on an electrical engineer, and he laid all this out for us in industry grade, VLSI layout software. In fact, there were parts of the circuit that didn't even occur to us we would have to add to what's already being used in the field. Because in the field, it's just being used to draw one random number at a time. But we wanted continuous bit streams. And for various reasons, we had to add extra circuitry that we didn't think about before to give us that functionality. So we built all of this in basically 22 nanometer CMOS. So in other words, we got energy and area estimates for what it would cost to make this device if it was in the same kind of chip you have in your laptop right now. We're really happy with that. But we also weren't all the way there because this particular design I showed you, there's really no room to put a spin transfer torque control here. So we can't tune the probability of the MTJ. It's just in its 50-50 state. And yet we need to be able to generate various levels of probability for the neural network to make sense. So to do that, we realized we could just go right back to CMOS. We could go back to these stochastic computing ideas. We decided that we would take MTJs, which give you each 50% probability. And if you just multiply those together with an AND gate, you get out a bit stream that represents a probability of 1/4. If you want 3/4, all you have to do is send the ones to zeros and zeros to ones. That's what a NOT gate does. And so by judiciously choosing which of these outputs you want and feeding them into more and more MTJs, you can use a very simple circuit to generate 2 to the n different probabilities using n stochastic MTJs. So we went ahead and built all of this as well in that analog design software in 22 nanometer CMOS. And then we asked, okay, how well did we do? Did the MTJs buy us anything? Turns out they did. So we compared this to what's called a linear feedback shift register. That's basically the electrical engineering standard circuit for pseudo-random number generation. It's what anybody would turn to for a pseudo-random number generation at low energy. And it turns out we do about a factor of 2 better in energy per random bit than the standard electrical engineering solution, which we were really happy with. And what we kind of learned from this was that, we isolated just the new behavior that we needed out of the MTJs and then did the rest with CMOS because CMOS is really efficient. But just this new ingredient of having access to true randomness let us build a much simpler CMOS circuit than what you would need if you didn't have access to true randomness in the first place. Now we can also go back and compare this to the analog design. We chose some generous resistances of 100 kiloohms and 50 kiloohms for an MTJ in this p-bit configuration, and found that it draws about 3.4 microwatts of power. So if you go back, you see that we were hovering around 10 femtojoules for our random number generation. The analog circuitry to reach that point of energy per random bit would need an autocorrelation time of the MTJ on the nanosecond scale. And that's because you're constantly using energy every infinitesimal time to keep this analog MTJ biased at a particular probability. But you're not really getting a new random bit every DT. You kind of have to wait for the characteristic switching time of the MTJ to pass before you can forget what state you were in before and count your next sensing event as an independent random draw. If you could get an MTJ down to this level of autocorrelation, you could indeed meet or surpass this energy efficiency. And I don't want to sell that field short because a lot of progress is being made on designing those types of MTJs. So that may be possible. And then you could use spin transfer torque control to gain analog control over your generated probabilities. I'll just point out that even if you could do that, you need to be using it in a circuit that can accept those random numbers at the rate you're generating them, or else you're again just kind of wasting energy. So people who are interested in these analog p-bit designs, there's a whole wealth of literature from Supriyo Datta's group and Karam Kamsari. They're not doing the same kind of calculations we are. They're building almost like analog models of physical systems and letting them anneal. So this analog behavior makes a lot more sense in that context. But in our context where we're integrating with CMOS, we found that the clocked pre-charged sense amplifier solution was far superior. And to summarize what we learned from this, basically there was this temptation because we had this Spintronic device and we know so much about the physics of the Spintronic device that we're tempted to use the physics for as many operations as we can. But it turns out that if you just isolate the one thing that makes the Spintronic device special and then let traditional engineering take you the rest of the way, you can gain orders of magnitude in energy efficiency. So that was the lesson we learned. And in the last couple minutes I have, I just want to return to the neural network. Because I told you about these MTJs and about what we were doing with these probability streams and using simple circuits to do arithmetic on them. I just want to quickly bring us back to the neural network. So remember, this was the fundamental unit of a neural network. You had these input numbers, they got multiplied by these weights, added up, and some nonlinear function was applied. In our case, we're using random bit streams to represent the inputs and outputs. And the weights will also use random bit streams generated by our random number generators to produce. We can multiply them by the inputs using these simple AND gates. And then we need some way to add them up and apply some kind of saturating nonlinear function. But that's exactly what an OR gate does. So this very simple circuit, just AND gates and an OR gate, is our neuron. And we thought that was really elegant, and we built a full neural network in simulation using these types of devices and asked, how well did we do? How much was the MTJ able to gain us compared to what's happening in traditional engineering fields right now? So this is kind of a series of points that represent the different configurations of our network. Basically, we're looking at how long we run our network for. Remember, the information coming out of the network is just draws a random process, right? Drawing from some stochastic distribution. So if you only wait 32 time steps, you only get to collect a little bit of data from the output. And that means that you may have sample error. There may be statistical fluctuations that obscure the answer that the network is trying to report to you. So if you wait a little bit longer and a little bit longer, you can start to increase your performance and drop your error, obviously at the cost of expending more energy. So we found that kind of saturated performance at about 256 time steps, but we decided to take this point at 128 time steps for a good trade-off between performance and energy per network operation. So that's this point, and we're comparing it to a bunch of other comparable neural networks, the exact same neural network with the same transistor models and everything from the computer architecture fields. What we see is that we do much better in energy per inference than these networks do. Note this is a log scale. we don't do as well in network performance, especially compared to this network over here. But we were kind of encouraged once we realized that most of these works are all coming from the same couple research groups that have been collaborating on optimizing their initial designs over the years so they arrived at this final optimized solution. So given that this was our first crack at it, we kind of hope that further optimization, and especially learning what it means to train a network based on OR gates, will help us improve the error while maintaining low energy per inference. So why would you use this kind of neural network compared to a traditional GPU or even CPU? Well, it turns out you get much better energy per operation, remarkably better, probably just because there's all kinds of stuff going on in the GPU that's so unrelated to the simple task that we want to perform. Our network is also able to perform a little bit faster than a GPU, though I would take this with a grain of salt. It's probably more like they're comparable, but we're still happy to be able to match the speed of a GPU using this design. Now, with that said, the accuracy is much higher in traditional neural network computing platforms, largely because nobody's thought about how to train a neural network based on OR gates. But a lot of people have thought about how to train neural networks that you can configure in GPUs. So we definitely lose accuracy compared to traditional applications. And of course, we're talking about something that you would have to commission taping out a chip, a $30,000 job to make one of these, whereas you could buy a GPU online. So why would you use one or the other? Well, if you're in a scenario where you have a small power budget, like in an implantable device or phone, and you're willing to get away with low accuracy, maybe because a 2% error missing a human face in a photograph, or a 1% deviation tracking somebody's heart rate for a non-critical application, like if you're jogging and want to track your heart rate, you can get away with low accuracy there. So that's exactly where the types of things we're thinking about could be useful. On the other hand, if you want to make sure you don't crash into another car or that nobody steals your data, you of course need the high accuracy, and so you would go for something more like a GPU solution. So for more on these trade-offs, especially thinking about the trade-offs between CMOS and Spintronic devices, and thinking about what it is that makes Spintronic devices unique and how we can isolate those properties to make energy efficient, effective device concepts based on Spintronics. I would encourage you to look at this paper that we published earlier this year based on this topic. We sent it around to some of our engineering friends. We wanted to make sure that it could be taken seriously by computer architects and circuit people. But we also went through great pains, being physicists ourselves, to try to make this accessible to other people working in Spintronics. So I encourage you to take a look. I'll finish by thanking my collaborators. This is me circled. Mark is my advisor, as well as Jabez. Adwet is our electrical engineering genius who did all the circuit design. Philippe works with these devices in the lab, and although we had no experimental results in this paper, a lot of his interrogation of these devices taught us a lot about what physical properties we could expect in realistic devices. And of course, Alice was integral in developing this project as well, but she's now at CNRS Thales, so she missed this great tie-dye picture. With that, I'll leave these conclusions up on the screen. Thank you for your attention, and take questions.
Thank you very much, Matthew, for this interesting talk. So we can now take questions. If you have a question, please use the raise hand feature as usual in the participants panel. If you can't find it, send me a private message through chat and I'll help you. First question, Axel, please go ahead.
Hey, Matthew, really a very nice presentation. I'm wondering, so what is the role of the fluctuation timescales in all of this? How well does that have to match your clock speed, for example, and all that? How critical are those?
Yeah, that's a great question. So, by the way, nice to hear from you, Axel. So let's see. I'm trying to see if I have a plot and a backup slide. But I think that I do not. So It depends how you're extracting your random bits. So I kind of mentioned that in the analog case, basically the autocorrelation time, the fluctuation time of the device is really just going to govern your energy efficiency per bit. In our case, there are kind of two time scales to compare to, right? There's the clock, as you mentioned. There's also the finite operation time of the sensing circuit. So let me go back to here. So, okay, the clock cycle, you want to be able to draw an independent random number on every new clock cycle. So it turns out we looked at the autocorrelation of the devices, and the autocorrelation turns out to approximately just be the sum of the mean dwell times in the parallel and anti-parallel states. So if you vaguely imagine it as an oscillator instead of a stochastic device, you basically need to wait one period before you sample it again. And that will give you very low autocorrelation and pretty good independence in your new random bit. Now, if you go too fast, right, if this thing is switching faster than a nanosecond, then you can kind of see the circuit dynamics aren't going to be able to come to equilibrium in time. Now, I don't exactly know how that would work. This is actually a really interesting circuit because as soon as the clock changes, you put the circuit in an unstable state, and it has to reach one of these states to come to equilibrium. So it might still work, but I wouldn't want to make that claim. So I think the switching frequency of your devices needs to be greater than a nanosecond to make the circuitry work, but your clock cycle can be no faster than one stochastic period of the device, one mean stochastic period.
Okay, thank you. Professor Hillebrands, next question, please.
Okay, yes, very nice talk. So thank you very much for this overview. The question I have is simply, I understand you use the MTGs as some kind of breakout technology to get out of the CMOS circle. But there are other methods or other approaches also around. Can you benchmark the performance of the MTGs compared to other ideas which are currently discussed?
That's a good question. So I assume that you're talking about other devices for that exhibit random telegraph noise?
Mm-hmm.
Okay. So yeah, that's a good question. So we talked about a couple different ideas within our group, and one of the conclusions we came to was that in our opinion, we didn't think of a very possible device. One device we were thinking about were basically, bad transistors.
Mm-hmm.
And although you can get pretty good energy efficiency and switching speed out of those, one thing that occurred to us was that, as far as we know, it's difficult to establish tight fabrication margins on that kind of device. Mm-hmm. Whereas fabrication margins for MTJ technology, at least for the devices that are being manufactured right now, which are admittedly not superparamagnetic tunnel junctions, but with even short-term MTJ technologies, people are able to get satisfactory engineering margins. And we looked at some of those margins and determined that the kind of circuits we were talking about would operate well and would tolerate those types of fluctuations in fabrication. Now, I can't really speak to what those margins look like in, defective transistors or in RTN from memristors. I've looked at some memristor random telegraph noise before, and at least what I was looking at seemed like it wasn't giving you a strong enough signal to have an efficient read circuitry. But okay, with all that said, I don't know a lot about some of these other proposals that are out there. So what I would say is that if you can find a device that has high speed switching, stochastic switching with low autocorrelation time, and that has an efficient sense circuit and can be manufactured within tight enough margins to guarantee uniform properties across a computational circuit, I think any device would be appropriate in this exact same scheme. I mean, frankly, all that matters in this particular sense circuit I have on the screen is that it's a resistor. So you could put anything there that shows random telegraph noise in a resistance.
Okay, thank you.
Sure. Thank you for the question.
Thank you. Shen, please go ahead with the question.
Thank you, Matthew, for the very interesting talk. First, actually, I want to ask about the estimation of the energy, because you compared it with energy in many of the devices with the conventional CMOS devices. For example, on slide 25, yeah, so on the figure on the left, and you compare this MTJ-based ones with the LFSR, how exactly was the energy calculated in the MTJ-based devices? Where does most of the energy consumption come from? If it comes from MTJ, is there anything like from the MTJ design that we can further reduce the energy cost?
Okay, that's a good question. So I can tell you exactly how these numbers were calculated. Actually, we calculated both of these numbers ourselves. So in both cases, we, I say we, but mostly a duet, our electrical engineering friend, designed these circuits in analog, industry grade simulation software. Now, those software packages do not include stochastic MTJs, but we had some collaborators who had developed a model for stochastic MTJs that could be used in this kind of simulation. So we put that in there. Everything else was just standard circuits and transistors. And to get these energy numbers, basically we run the circuit and we look at two things. One is ohmic losses due to current passing through the resistors, right? It turns out that's actually pretty small. And the reason that's pretty small is because if you remember how I kind of explained the way the circuit works, you're only using a tiny amount of charge that's left over from some tiny capacitance on the transistor to establish this race between RC times. So you actually have very little current flowing through the resistors. Most of the energy draw is actually a CV squared energy from charging and discharging of the transistors. So what we do is in these simulations, you basically, you could do it more intelligently, but I'm pretty sure what we did was to take the worst case, which is just to assume that every wire in the design basically switches from high to low voltage, like with 50% probability, on every clock cycle. So that kind of mimics the charging and discharging of the capacitors everywhere in the circuit and gives you these energy estimates. And then you just add it up for one clock cycle, and that's what we're reporting. So we did that both for both of these. So in terms of the MTJ design, if you made the resistance higher, it, I guess would nominally reduce some of the ohmic losses, but it would also increase the RC time, which isn't a big problem. I mean, I think we used a kilo-ohm resistor here, and the RC time, is like 1 nanosecond. It's not a big deal. If you made it really large, I guess that might start to become a problem if your switching time of the MTJ went below that RC time. Of course, having a larger TMR is also pretty much, as always, going to be helpful. And that's because, remember, these devices in reality, and we're imagining a circuit where we need, I think, like 500,000 of these things on a chip to execute our neural network. They're going to have fabrication margins. And so you need to pick one reference resistor that's guaranteed to be between these states for every single device in your circuit. So a large TMR will kind of guarantee that you have space to place the reference resistor between them. And of course, the last thing I would say is that if you can increase the switching frequency, then you can lower the clock frequency and just make these things go faster and faster at the same energy expenditure per bit, which is always going to be favorable. That is a challenge that a lot of people are working on. I mentioned some people are working on low barrier magnets, and they're essentially thinking about having not even a two-state system anymore, but just sort of a free, easy plane where the magnetization drifts very quickly, and you can extract randomness from that. But we like to think of this two-state model, and ideally we'd like to have as rapid switching as possible between two well-defined states. So I guess those would be my ideal characteristics.
Thank you very much.
Sure.
Thank you. Beng, please go ahead with your question.
Yeah, thank you, Matthew, for your interesting talk. I have a follow-up question on the energy. You mentioned you have 10 femtojoule per bit, but if I'm thinking of MTJ, STT, the current density is 10 to the like mega amps per square centimeter, and it's hard for me to get to femtojoule. So how could you tell me? But I agree with you that many papers report femtojoule per bit, and why is there a difference?
Okay, so let me see if I can understand your question. So you're quoting a particular current number for running the current through. I think I understand your question. Yeah. So let me find the right slide. I guess it's kind of this one, right?
Yes.
So, right. So the question is, how do I get 10 femtojoules per bit? So what we came up with, the more fundamental physics number that we came up with was really this power. And the way we arrived at this power was by choosing these for their resistances, which I think are probably a little bit high, but we wanted to err on the side of favoring this technology. And we had to choose certain transistor characteristics and put things in the right way in the p-bit circuit to make it run in an optimal way. And once you calculate that, on average, when the MTJ is in the 50% probability state, this is the ohmic power dissipation through the MTJ, not counting any of the transistor charging and discharging, not counting the analog current source you would need to drive the circuit. This is just the ohmic losses. So I don't know off the top of my head if this agrees with the current number you're thinking about or not, but the way that we get to this 10 femtojoules per bit is by assuming that the switching frequency of the MTJ is on the order of a couple nanoseconds. And what that means is that you can fairly extract a new random bit every 3 nanoseconds. Now, to my knowledge, I may be wrong, but to my knowledge, we don't have any real SMTJs in academic labs that reach this number. I know the ones that we work with are more like kilohertz. So, if you had kilohertz stochastic switching instead of gigahertz, you would be spending more like, 10 to the 6 femtojoules per bit. So I think that a lot of the claims in the literature about getting this very low energy per bit basically arise from dividing this power by a lot of random bits that one assumes could be obtained within a unit time period, based on theory work that suggests that you might be able to build such magnets. I don't want to say it's not possible, but that's where those low energy numbers come from. Does that make sense?
Yes. Thank you.
Sure.
Okay, thank you. I have a clarifying question. So when we talk about this autocorrelation time, is there some sort of physical source of the correlation, or is it just a mathematical fact that when you have a certain time decay constant, your process will automatically have an autocorrelation?
I mean, in the purest form, it's the latter of those. But ultimately, of course, it comes from the physical system, from the physical autocorrelation. It's kind of weird in these two-state systems to think of it as physical autocorrelation. I think because we're not used to thinking about the physics of kind of two-state systems in this way. So yeah, I'm thinking about it like a mathematical autocorrelation. You know, to analyze the autocorrelation of our devices, we just generated a bunch of random telegraph noise and, you know, use the autocorrelation function in Mathematica. Now, with that said, the engineering, well, the science at this point that's going into these low barrier magnets, I mentioned a minute ago, those kind of rely on having an easy plane with no easy axis. So you just get wandering of the magnetization in a circle. And in that case, I think it's much easier to see the physical connection to autocorrelation of the physical state in time. But in those systems, you know, they also need low autocorrelation in order to generate, you know, many random bits per unit time.
Mm-hmm. Okay. All right. Are there any further questions? Please raise your hand if you have one. If not, let's thank Matthew for this interesting talk. You can use the reaction button